today we'll be talking about imitation learning. Great. So as a partial recap from last time, we started talking about some of the notation that we use for representing behavior and formulating problems as a decision-making problem. We talked about states and observations, where we either have access to something that can fairly completely represent the state of the world, or a more partial representation that we will refer to as an observation. We also will be representing actions or decisions with AT, and then we can think about a trajectory as an example of behavior that we've taken over time. We also introduced this notion of a reward function, which is how good is a given state and action. And lastly, this kind of notion of a policy, which is either conditioned on the current state, what actions do we want to take, or conditioned on a history of observations, what actions should we take? And usually this policy is the behavior that we're trying to learn. We briefly mentioned how this kind of policy can be represented using a generative model, and we'll actually touch on that a little bit more today. And the last thing that's not on the slide is that we talked about how the goal of reinforcement learning problems is usually to maximize the expected sum of rewards. And today we'll be talking about one way to do that by trying to imitate a good policy. And in particular, the plan today is to go over some of the basics for imitation learning. Then we'll talk about learning expressive policy distributions and why that's important for imitation learning. Then we'll talk about learning from online interventions, and time permitting, we'll talk a little bit about how to collect demonstrations in the first place. So some of the key learning goals, this is a little bit, in some ways, kind of orthogonal to the main topic of the class, but it's actually very important to understand in order to get performant imitation learning systems. So we'll be talking about how to represent distributions using neural networks rather than deterministic functions. We'll also be talking about why expressive distributions matter for imitation learning, and one challenge that can come up with imitation learning, which is compounding errors and how to address compounding errors. Great. So what is the goal of imitation learning? Like the goal of reinforcement learning, we want to try to achieve high reward. We want to get a good policy that can do the task well. And the way that we'll try to do that is we'll assume that we're given some trajectories that are collected by an expert. This is our data. And we'll refer to these trajectories as demonstrations. So it's kind of like a special kind of trajectory that is demonstrating how to perform the task. And we'll use D to denote these demonstrations. Like a trajectory, it'll be a sequence of states and actions. And as an example of what this demonstration data might look like, if we wanted to learn how to autonomously drive a car, we could have demonstrations that are in the form of people driving cars, because people are pretty good at driving cars most of the time. And so we could record from the sensors on a car, as well as record kind of steering commands, acceleration, and so forth. And using a data set of human drivers driving, we could then try to mimic that in order to train an autonomous driving agent. Now, we don't know exactly how humans drive. We don't know the policy that humans are using in order to drive. So we can think about this demonstrations data set as being sampled from some unknown policy PyExpert. And then the goal is to learn a policy that performs at the level or similar to the level of the expert policy by mimicking what's present in the demonstration data set. Cool. So this is the problem setup. Now, let's think about kind of version 0 of how we could try to do this. So kind of a very simple way that we could do this is kind of first, we're given our demonstration data set. So this is some data set that contains state action pairs. We can think of, these are each of the state actions in each of the demonstration trajectories. And then we could say that we want to train some policy to mimic the demonstration. So we would be training some policy. And in particular, we could think about the the actions that this policy is going to take. So if we were to take one of the states in our demonstrations and run it through our policy, then we would get some sort of predicted action A hat. So let's say that this is sampled from pi theta given a state in the demonstration. And then we could try to basically say we want this predicted action to be as close as possible to the action that the demonstrator took. So we could then minimize the difference between the predicted action and the action in the data set. And we could do this minimization over all of the states and actions in our demonstration data set. Once you train a policy such that the predicted actions are as close as possible to the actions in your data set, then you can just deploy your policy. This is a policy that should be mimicking the actions in your data set. This is version 0 of imitation learning. So given demonstrations collected by an expert, you essentially do supervised regression to the expert actions. If your policy is a neural network, this means doing a forward pass on, you sample a mini batch from here, do a forward pass on your neural network to get the predicted actions, compute the loss, and then back propagate the loss into the parameters of the neural network. And you do that iteratively with your favorite optimizer, some form of stochastic gradient descent, in order to optimize your policy. So it's essentially a form of supervised learning. And then from here, you can then deploy your learn policy, and it should be able to mimic the expert and do something sensible. Yeah, so in this case, we're considering a deterministic policy. Yeah, and we're just essentially, doing L2 regression. I guess here I wrote it as a stochastic policy, but let's correct that, and let's have this be a deterministic policy. The expert might not be deterministic, and that might lead to some issues. So let's actually talk about that a little bit. So what could go wrong? Let's go back to our driving example. So we have a data set from human drivers, and we recorded the states or the observations. We recorded the steering commands and any other actions that we might want to use. And let's say that for this particular car, in some cases, some human drivers might decide to go straight, and other drivers might decide to merge left, maybe because they want to move to a faster lane. So our data set might contain both examples of going straight in situations like this and examples of merging left in situations like this. Now, a question for you. If you train a policy with L2 regression on a data set that has these kinds of examples, what would a policy that was trained with L2 regression do in a situation like this? Yeah, so the policy might go to the middle of the two lanes. And let's see why that is. So we, in this example, say we have the steering command. And if we thought about the distribution over actions that are covered in the data set, for drivers that chose to go straight, their distribution of actions would look maybe something like this, where this is like 0 steering command. This is like kind of staying straight. And for the drivers that chose to merge left, their distribution over actions for the steering command might look something like this. So this is the probability over actions. And then if we think about these are kind of the two examples. This is if they're deciding to merge left, they maybe have a steering command of -2. This is if you stay straight, that might have a steering command of 0. And then in your data set, the kind of overarching distribution over actions represented in the data set might look something like this, where maybe more likely people are to go straight than to merge left, but you get this kind of multimodal distribution that has two peaks, one at going straight and one at merging left. And then when you use L2 regression to try to fit this kind of fit this data, what it's going to do is it's going to predict the mean. So it's going to predict the mean action. And in this case, the mean action would be something like here. And that would be probably a not very good action to take, because that might kind of straddle the lines on the highway. And also we can see that this action actually has very low probability under the data distribution. So it's also kind of objectively or mathematically a poor choice, because it had low probability under what the data was doing. Yeah, so L2 regression is the equation from the previous slide. So basically minimizing this squared loss between the predicted action and the true action. And then the other question was, what is the difference between the green and the red here? So essentially what I'm drawing in the green is this is the distribution over kind of expert actions. Maybe I'll use expert to refer to that, conditioned on only the data that chose to go straight. The blue is the distribution over expert actions if they choose to merge left. And then the red is the distribution of actions represented in the data set for a given state. So this is, the red is actually what your data looks like. And this is, I'm kind of just showing, this is what the distribution looks like for kind of one subset of drivers and the other subset of drivers. You're asking, can you sample from the data set and do what was in the data set, basically? Yeah. So the tricky thing with sampling from the data set and doing what's in the data set is that that would look kind of like a nearest neighbors approach, kind of within the realm of machine learning. And it is in some ways a viable approach to a number of machine learning problems. But one big challenge is that ultimately when the car is driving, or when you're kind of have some sort of autonomous driving agent, it's going to face scenarios that are different from what's in the data set. And when it's in those different positions, you won't necessarily have examples in your data set that you can just pick from. So you won't necessarily be able to say like, oh, I saw what the expert did in exactly this situation, because ultimately you'll be evaluating scenarios that are different. So what would you do if the actions are not numerical? We will also, in like a slide or two, we'll talk about discrete actions as well. So to go over this example on the slides, we could say that the data for staying straight is in yellow. The data for merging left is in blue. The combined data set, maybe because more people decided to stay straight, is shown in black, the black dotted line. And then if we train a model to minimize the L2 error, then the deterministic policy will choose to take an action that's right here, which is the mean of the black distribution, which has low probability under the data. Now you might be wondering, how often does this actually happen in practice? So like this is kind of, maybe you might think that this is kind of a contrived example where there is kind of variability in what people would do. It turns out that this actually happens all the time. People and demonstrators often do things in different ways, not just in driving and not just in like key decision states. And this happens especially when data is collected by multiple people, because people have different preferences. They have kind of underlying ways that they like about doing things, and you can't directly observe all of those preferences and all the things that might affect their behavior. And so as a result, there are some scenarios where if you have like one expert policy that's kind of always takes a consistent strategy, it's okay to use a deterministic policy. But in many other cases, it's actually very important to make sure that you account for this kind of multimodality in the data. And so the natural question that arises from here is, instead of just learning the mean, could we actually learn to represent more of the distribution of the expert data and not just the mean? Cool. And so this is where kind of learning distributions with neural networks comes in. And in particular, let's start a new whiteboard. So in the case of the deterministic policy, we had some neural network. I will use a box to represent a neural network. And we're taking as input some state, and we're outputting the mean action, kind of the mean of a distribution. And so because it's only representing the mean, it's hardly a distribution at all. And instead, what we'd like to be able to do is have this neural network actually output the kind of parameters of a distribution over actions. And if it can output those kind of, if it can output a distribution over actions, then we should be able to capture more than just the mean. Cool. So this is often the way that we try to learn distributions with neural networks, is we actually output the parameters of those distributions. So you can think about it as this. You have a neural network, outputs parameters. If the distribution class that you choose is very expressive, then you should be able to get an expressive distribution as output. Now let's think about a couple examples of what this might look like. So if your actions are not continuous, and if instead they are discrete actions, so maybe you're trying to train a policy to play a video game like Super Mario, then the actions might be something like up arrow, down arrow, press A, press B, right arrow, something like that. And what you could do is the neural network could output is basically this categorical distribution over actions, where it's going to, in this discrete case, it will output the probability of the first action, the probability of the second action, the probability of the third action, and so forth. And so you can think of this sort of as a classification problem. And this distribution is actually maximally expressive. And what I mean by that is that there isn't any distribution over actions that this cannot represent. Because it's a fairly simple kind of categorical, or pretty simple set of discrete possible options. So this is actually really nice. We can get a really expressive distribution this way. Unfortunately, a lot of the world is not just one-dimensional discrete action choices. We often have much more complex actions. And that's why we need to think about how to model distributions over those actions. So if we move towards continuous actions, like in a driving scenario where you have steering commands, for example, the most natural thing to do is to use a Gaussian distribution. We talked about outputting just the mean of a Gaussian distribution, which corresponds to minimizing the squared error. But you can also have the neural network output the variance. Unfortunately, if you have it output the variance, it's not going to do anything particularly helpful. In this example, it'll just output a wider variance Gaussian in order to try to cover more probability mass. And it's not very expressive. And so we want to be able to use distribution classes that are more expressive so that we can try to ultimately get actions that are high probability. Yeah, so the question was, if we have some action distribution that looks like this, for example, would we be happy if we can perfectly model this? Or would that still lead to issues where you might have like an indecisive policy that chooses one mode and then chooses another mode? The answer here is that if you have a good state representation, then you should be happy. And in particular, say you modeled this perfectly, and for example, you chose like this, and then you start merging left. Then if you know that you've started to merge left and your velocity is moving left, then the data should continue moving left. And so then at that point, the distribution over actions should look kind of something more like this, once you are in that state at that point. So if you have a good demonstration data set and a good state representation, if you perfectly model the demonstrations, you will get a good policy out. So the question is the only goal in imitation learning to mimic the expert, or is there some assumption that the expert was maximizing some reward? Generally, you kind of assume that what you're trying to imitate is good. But it doesn't necessarily need to be the optimal policy. And in many cases, like many real world practical messy scenarios, getting the optimal policy is like hopeless in some ways. So yeah, generally we assume that you're trying to mimic something good, and really the focus is on trying to imitate that. Yeah, so the question is, in this case, like, are we happy, if we do this perfectly, and are we happy with sampling a mode that is underrepresented? There are scenarios where you might want to try to essentially do better than the expert, and maybe in some cases this mode is actually better, or maybe in some cases this mode is really better. If you want to outperform the expert, that's more where reinforcement learning comes in and other tools come in. You could also try to curate your data set to try to contain more of the stuff that you think is better. But yeah, with imitation learning, generally everything that we'll talk about in this lecture is trying to meet expert performance or meet the demonstrator performance and not exceed it. Yeah, so the question is, should the parameters of the distribution over actions be state dependent? And yeah, absolutely. I've been writing this as kind of the parameters of P of A, but everything here is implicitly dependent on the state, because this is the output of a neural network that was conditioned on the state. And so in some states, it might choose to output a distribution that's really multimodal. In other cases, it might choose to output a distribution that is much more unimodal. Cool. So let's talk about some more interesting expressive distributions with neural networks. And some of these will build upon tools in generative modeling. And in particular, if we think about some examples of generative models, we won't go into all the details of these. But one example of a generative model that you might have seen before is called a diffusion model. And this is a model that can output and generate images of different people. It can be used to generate videos and so forth. It's very popular for generative models over visual data. And the thing that's really cool about these kinds of image diffusion models is that they are able to represent a very diverse distribution over images, including images that are completely different from one another. Another example of a generative model is an autoregressive model. You can think about this as essentially like what happens with language modeling, where you're predicting one kind of token or one word at a time. And this is also a really powerful model, and it's much more powerful than just outputting the distribution like at the mean invariance of a Gaussian, and much more powerful than outputting, for example, the categorical distribution over one dimension. So you can think about these two as most typically used to represent either the probability of an image given a text description, or the probability of the next word given the word so far. And the reason why they're often used in these contexts is because these are very common problems that people work on a lot, and also because they're very well suited for addressing these kinds of problems. But you don't, the underlying technique behind image diffusion models and autoregressive models is extremely general. And you can use the same idea to learn a distribution over actions given observations or given state. So let's talk a little bit about how we might use some of these tools to learn that distribution. So our goal is to approximate P of A given S. One example, one kind of maybe form of generative model that's simpler than those two that we'll start with is a mixture of Gaussians. And a mixture of Gaussians is already a lot more expressive than just a single Gaussian. And so it's a case where we're trying to model a distribution as a combination of Gaussians. And so in this case, instead of just having the neural network output mu, we'll have it output the parameters of a Gaussian mixture model distribution. And so in the case of a DMM, it will output the mean, standard deviation, and weight associated with one Gaussian, also the mean, standard deviation, and weight of a second Gaussian, and so on. And you might, if you have n different components, it will output n different parameters for different Gaussians. Yeah, so the question is, can we elaborate more on what does it mean for these distributions to be more or less expressive? Yeah, so essentially it is referring to if you have some underlying distribution, it's like how maybe I'll actually rephrase it slightly differently. So one way to think about it is it's essentially the number of different distributions you can capture, perfectly with that chosen representation. And so if you only use a Gaussian, then you can only perfectly model Gaussian distributions. Whereas if you use a Gaussian mixture model, you can represent any individual Gaussian, but you can also represent any distribution that can be represented perfectly as a combination of Gaussians. And so it's strictly more expressive than using a single Gaussian. Now, in some cases, it can be difficult to compare two different distribution classes, because in some ways some might be more expressive or less expressive. But in the case of Gaussian mixture models, it's strictly more expressive than a Gaussian. Yeah, the question is, do you need to pick the number of Gaussians ahead of time? Yes, you do. You can think about it as a hyperparameter, and you could experiment and look at how well are you fitting the data with different numbers of mixture components. Okay. And then there's two other examples of generative models that we could use. The second one is autoregressive, discretized and autoregressive, which is just like language models. And the third would be to use something like diffusion, but diffusion over actions instead of diffusion over images. And so we talked a little bit just now about mixtures of Gaussians, where we'll be outputting basically the parameters of a Gaussian mixture model. Now let's talk a little bit about kind of a scenario where we could try to use an autoregressive model, like a language model, in order to generate action. So in this case, there's a couple scenarios where you might want to use this. So you might be in a scenario where your actions are already discrete, and you actually don't need to discretize in that case. Or you might be in a scenario, but where it's multidimensional, or you might be in a scenario where they are actually continuous and multidimensional, and then you need to discretize or tokenize first, and then use an autoregressive model. And so if we think about this back in the driving example, so this will be, if we use discretize plus autoregressive. In this case, let's say that we're in the driving case, and we'll just consider a simplified driving case where the first action is the steering angle, and the second action is the acceleration. So if we wanted to represent a distribution over these actions using an autoregressive model, there's two things that we would want to do. The first would be to discretize, and the second then would be to formulate the autoregressive model. And in particular, when we use autoregressive models, it means that we're going to be essentially predicting one dimension at a time. So if we first want to model a distribution over the first dimension of the action, what we would do is, in the case of steering, so we have P steering. Say that we wanted our prediction to look something like this. Now a Gaussian can't represent this, and so we would choose to discretize it and represent a discretized distribution. And what that would look like is essentially kind of creating bins for the different steering angles. And you would then output a probability for each bin. And then this kind of something that looks a little bit closer to like a staircase, these bars would be the distribution that you're actually using to approximate the original distribution. And so you could then, in this case, output, so for the first dimension, you would be outputting each of the probability values for each of these bars, like the height of each of these bars. So this gives you a fairly expressive distribution over angle, and then you could choose to have a more fine discretization or a more coarse discretization. And if it's more fine, you get more expressivity in terms of what you can represent, but you also have to output more numbers, so there's a trade-off there. And then once you output a distribution over the angle, then you would want to output a distribution over acceleration. And in particular, in the case of merging left versus going straight, if you're merging left, probably you would be accelerating more because there was a car kind of back into the left, whereas if you're going straight, you're probably more likely to be kind of keeping your current speed. And so there's essentially kind of we want our distribution over acceleration to be conditioned on which steering angle we chose. So what we will do is we'll predict kind of P angle, and then we will sample a steering angle from this. We'll refer to this for now as AT1 because it's the first dimension of the action. We'll sample it from this distribution here. And then we want to get a distribution over the second dimension conditioned on the first dimension. And to do this, we'll then pass our predicted action or the sampled action back into our model and then have our model output another distribution. And in this case, if you are conditioning on AT1 equals maybe an angle that's like -2, so something more left, then you might output a distribution over acceleration that is kind of more, has more probability on higher accelerations versus if you condition on a steering angle that is something more like 0, then you might output a distribution over accelerations that is smaller. Yeah, so the question is, how do you build your training data when you are discretizing like this? So to do this, let's see. So when you build your training data, you'll have the state action pairs, and you'll be sampling state action pairs. And in order to kind of convert it into something like this, what you'll do is you'll sample a state action pair, and then you'll bin the action according to your binning strategy. And then you'll apply a loss to that is between the model's predicted distribution and the sampled action, which would be like one of these bins. And the loss, you can actually just use the cross entropy loss here. And so you can think about it as you're doing a classification problem for each dimension of your actions. One other diagram that I think would be helpful here to think about how we go about doing this is when you have a model that's kind of autoregressive, that's predicting actions, you often use a sequence model. And so if you think about kind of a sequence neural network, something like a transformer or something like that, you would pass as input your state, and then you pass as input, and then you're kind of predicting a distribution over the first dimension of your action. So this is kind of a distribution over steering angle. Then you would then kind of sample from this distribution, and then you'll pass this this sampled action or your kind of chosen steering command back into your model, and then output the distribution over the next action. And this is exactly how language models work, where you'll have some sort of kind of beginning token, you'll predict a distribution over the next word, you'll sample a word from that, pass that sampled word back into the model, and then predict a distribution over the next word. Except now we're doing it over dimensions of our action sequence rather than over different words in a sentence. Yeah, great question. How do you determine the order of these different dimensions? In language models, it's very natural because like there's a natural ordering to like words in a sentence, for example. Although even across different languages, there's some variation there. It's something that generally you kind of pick by hand. You could also, in some ways, treat it as a hyperparameter. In other cases, there might also be somewhat natural choices for the ordering. So if you're controlling a robot arm, for example, you can kind of go down what's called the kinematic chain of a robot arm, where you start with the kind of the base dimension, and then you go to the next joint and the next joint, and so forth. The good news is that in principle, the kind of the expressive power of this distribution doesn't change with the order. Essentially, your goal is trying to represent the full joint distribution over all dimensions. And the only reason why you're doing kind of an ordering here is because if you tried to represent kind of a joint distribution over all the dimensions at once, there's a lot of kind of pairwise probabilities that you would have to predict. And it's a lot more efficient to do it kind of one dimension at a time to represent the full joint. Yeah, so the question is, in the case of like a video game, it was pretty discrete. Here we're in a more continuous case. Are we discretizing, like whenever we want to use an autoregressive model, does that mean we should be discretizing, right? Cool. So there's actually kind of two reasons to be using discretization. One reason to use discretization is it allows you to model very multimodal complex distributions. And so you can, these bars can be any height that you want. And so it actually can model things that are way more expressive than a mixture of Gaussians up to how fine your discretization is. The challenge with discretization is that if you have like a lot of bins, like you might have 100 bins for one dimension, and then you're trying to represent like a, 10-dimensional action or something like that, then the dimensionality of your discretized actions is going to blow up. If you try to model all like that full 10 to the fifth matrix over probabilities. And so using an autoregressive model helps you deal with that dimensionality. You could, in principle, also use an autoregressive model with like a mixture of Gaussians, for example. And that would be like completely fine as well. This is, it's not like a common choice per se. Because if you're going to go through the trouble of using an autoregressive model, usually discretization is like a pretty powerful choice. But yeah, you can also use it with like a Gaussian mixture model or Gaussians or something like that. Yeah, so the question was around how we actually kind of train this, and maybe let's just like walk through how we go about training this. So it's actually going to look, let's walk through how we train it. So we're given some data set. So we're given some data set that has state action pairs, and we're going to want to train our neural network, and we're going to follow a typical way of training neural networks, which is to sample an example from your data set, or sample a mini batch of examples. I'll write it up for a mini batch size of 1, just for simplicity, but you can kind of extend it. So we're going to be sampling a state action pair from our data set. And once we sample this, we will essentially be running a forward pass through our network and a backward pass through our network. And the key question that comes up is like, doing the forward pass is kind of fairly straightforward. And when we do the forward pass, we'll be getting kind of some probability over the actions of each dimension. And then we need to figure out what should the objective be. And the objective there's actually kind of a common objective that we can think about for all of these generative models. And that objective is that we want, we're outputting these kind of probability distributions. We want to be maximizing the probability of the actions represented in the data. Or equivalently, we'll write this as minimizing the log probability of, I'll write this as pi theta of A given S. And this is with respect to theta. And so what this means is we're going to be evaluating how likely is the action that was sampled under our policy. And then we'll be trying to make the probability of the action in the data set as high as possible, or the negative log probability as low as possible. Now, in practice, what this log probability looks like is going to be different for different models. For a Gaussian mixture model, what you'll do is you can write down the probability density function for a Gaussian mixture model, and then just differentiate with respect to the mean, variance, and weight that is outputted by the neural network. And for the case of a kind of the autoregressive model, it's a little bit different. So what this looks like for the autoregressive model is we will have, we essentially get like the probability of AT1 and the probability of AT2 given AT1 and so forth. And this probability for this first dimension, it will just be the cross entropy loss. That corresponds to trying to maximize the log probability of this value for a discrete categorical variable. And for the second dimension, that's where things get a little bit more complicated, because you'll have this will just be the cross entropy loss, but you need to figure out which action you want to use here. And oftentimes you will use the action in the data set. So for the inputs, you'll often actually pass as input the state and the dimensions that were chosen in the data set. And then for each of these probabilities, you'll be applying the cross entropy loss and backpropagating the cross entropy loss back into the network. And then at test time, you'll then actually be using your own predictions and passing your own predictions into the neural network. But this is really this objective right here is really the core loss function. And this corresponds to a form of cross entropy loss for discretized distributions. And for Gaussian mixture models, you write down the PDF and differentiate. Yeah, so the question was, it seems a little odd to discretize and do a categorical distribution over a continuous variable, especially given that a loss function like cross entropy won't take into account the fact that two bins are like, that sort of error is probably less costly than an error that is, that for two bins that are like very far apart from one another. This is kind of one downside to using discretized, kind of discretized actions. In practice, often that sort of distance is something that is fairly quick to learn. And so the outcome is often, still pretty good. But you might need more data, and how fine your discretization is a really important hyperparameter, because if it's too fine, then it'll be very hard to get signal, because, if you're off by one, you'll get like zero loss function. There are also other things that you can do to try to smoothen out the data, and smoothen out the labels so that, the label isn't just, like a one hot vector. You can kind of smooth around it a little bit. So that's one thing that can also help with that, although, it's a little bit more advanced. Oh, yeah, awesome question. I didn't actually get to write the third example. And so, yeah, so when you are outputting the probability over the third action, it will be conditioned on everything so far. And often the way that you do that is, if you're using a sequence model, you can then output the prediction, like a sample from this distribution. So AT2, and then output the probability over the third action right here. And if you have a sequence model that takes into account everything from the past, then it will already condition on all the actions so far. So how does backpropagation handle this when it's discrete? So only the output is discrete. And so you can think about it as a classification problem. And so if the weights are discrete, that's bad for backpropagation. But when it's only at the labels, you're only just computing the loss function on those discrete variables. And then that loss is you can backpropagate in a direct way. And that's because you're comparing the output is outputting a probability and computing a loss on that probability, and then you can backpropagate that loss on that probability. So the outputs are actually still continuous values, because you're outputting the height of each of these bars. Cool. So this is a visualization of this kind of discretized case where we're outputting the first dimension, the second dimension given the first dimension, the third dimension given the first two dimensions of the action, and so forth. And this is very scalable. It allows you to handle like fairly long sequences of actions, similar to language models. The last thing that I put up on here is diffusion. Diffusion is also a very appealing choice, especially for continuous actions. It can model very complex distributions over continuous variables, including high-dimensional continuous variables like images or actions. And it does so by using this kind of denoising process where you start with complete noise and denoise it iteratively to make it a less and less noisy version of the action to ultimately generate, hopefully, a clean action prediction. And one thing that's kind of notable is both this model and diffusion models do have some sort of iterative process. In the case of autoregressive models, it's iterative over the dimensions of your prediction. And in the case of diffusion, it's iterative over this denoising process. Now, one question I have for all of you. So we've talked about these more expressive distribution classes. And none of what we talked about has actually really changed the architecture of the model. And I'm curious, one very important question is, instead of having these more complex distributions, we could just still use the L2 error, like the L2 norm as the loss function, but just make the neural network bigger. And bigger neural networks are generally more expressive than smaller neural networks. So does anyone have thoughts on how what we talked about here is different from just making the model bigger with the L2 loss? Yeah, so in the driving example, even if you make the network really, really large, it's still going to output just the mean. It might output the mean very, very accurately, but it doesn't actually change its ability to represent a more complex distribution. And so the expressive power of a distribution that you're trying to represent is actually, in many ways, separate from the expressive power of the function itself. And if you think about kind of this picture again, where you have a neural network that's outputting parameters of a distribution, there's the expressive part of this function of how many functions can you represent that go from S to parameters? And then there's the expressive power of this top part, that how many different distributions can those parameters even represent in the first place? And this is a really important point, where kind of neural network expressivity is often distinct from distribution expressivity. Yeah, so the expressivity of this output, the expressivity of the distributions that it can represent is kind of captured by what kind of distribution you're allowing it to represent. And if it only outputs the mean invariance, it can very expressively represent functions that go from state to mean invariance, but it can't represent anything more complex than a Gaussian. Okay, so we walked through this a bit. So we are given some demonstrations. We're trying to train a generative model over actions. And this is trying to minimize the log likelihood of the negative log likelihood of the expert's actions given the states in the demonstration. And so this equation looks, maybe a little bit complicated, but the log pi is the log probability under the policy. The blue part is the demo actions that are sampled from the demonstration data set. And this probability is under the policy that we're trying to learn. Cool. And then once we fit this, we should have a policy that's better at actually matching what the expert is doing. And as a result, it should be better at performing the task. Okay. So now why did we learn all this? How well does the generative model work compared to just using an L2 loss? There's a couple of works that have evaluated this more explicitly. So here's a transport task where you need to have one robot kind of transport a tool to another robot, and the policy is controlling both of these robots. And we'll be comparing diffusion and a Gaussian mixture model. Diffusion is a lot more expressive than what you can even represent with a Gaussian mixture model. And we'll be looking at two different demonstration data sets. One was a data set that was just collected by one person. And then the other one is a data set that was collected by multiple people. And we'll look at success rate. And when we use diffusion, we see that on both data sets, it's able to do pretty well, although it does degrade with multiple humans in the data set, which means that as you add more diversity in the data set, performance can go down. And with the Gaussian mixture model, we see that first it does worse than diffusion. So expressivity is very helpful. Expressive distributions is very helpful. And second, it actually goes down a lot more for the multi-human data set, which means that the expressivity of the distribution is especially important for data sets that have more different kinds of behaviors in them. We can also see this on a real task on a real robot. So this is a task that's actually pretty difficult, hanging a shirt on a hanger. It was collected by, the data set was collected by lots of different people, because it's actually a pretty large data set. And once you scale up, it's very hard to have a single person with one consistent strategy collect all of your data. So it has different people and different strategies. And it compares using either diffusion, which is very expressive, or an L1 loss, which is a deterministic policy. And what we see first, it's not as successful as the simpler simulated task. But here we see again that like having a expressive distribution is really critical for being able to do the task successfully. And if you just use L1 loss, the success rate of the policy drops by nearly 50%. Is there any scenario where you'd want to use a mixture of other models instead of a Gaussian? Oftentimes other models are might already like be quite expressive. So not to my knowledge, but it's not without not like completely inconceivable. Yeah. Okay. Now, if you actually look at some of the like big models that people have been developing in robotics, they build on what we covered so far in lecture. And so these are kind of foundation models trained on lots of different demonstration data sets by companies like NVIDIA, Figure, Pi, and this kind of open source vision language action model using expressive distributions when you have large scale data sets is a key component of these models. And if you look at some of the big models that people have been developing for autonomous driving at Waymo and Wave, the first one uses discretized and autoregressive prediction, and the second one also uses discretized actions with autoregressive prediction. Great. So a summary so far of what we've talked about. If you have data from one consistent demonstrator, you should learn a unimodal policy distribution. If you have multimodal data from multiple demonstrators, you should learn a distribution. You need an expressive generative model when you have data from multiple people. Very important. And one other thing that I'll mention here is that the algorithm is fully offline. And this is getting into a notion that's very important in reinforcement learning more generally, which is offline algorithms are a bit different from online algorithms. So offline algorithms use only an existing data set, and they don't use any new data from what you're learning. And online means that you're using new data from your learned policy. And this distinction is important in a couple different ways. Online means that you're going to have to actually kind of recollect data as you run the algorithm. And so this can be expensive. It can also, if your policy might be like undertrained in some scenarios, it might be unsafe to run your policy. Like if you're in like a medical domain, for example, you might not want to collect online data from a policy that doesn't work fully yet. And so there's kind of, thinking about offline algorithms and online algorithms is generally, it's a key distinction and a key way to think about different algorithms. So for what we've covered so far, we also, we don't need any data from the policy, so this is offline. We also don't need to define a reward function. Last time we talked about defining reward functions for some examples, and we talked about how, in some examples, it might be kind of hard to write down the reward function. So this is pretty nice. Like in driving, you don't have to write down all of the ways in which you might want it to drive. The downside is that you might need a lot of data for reliable performance. You might need a lot of demonstrations. And that ties into how we might try to learn from online interventions. Yeah, so the question was, for the kind of previous videos that I showed, imitation learning seems straightforward. Like, what is like the research in it? And is it just doing what we talked about today? There are a couple, well, I guess there's a number of different things that went into those different examples. So I can walk through, maybe a couple examples. So in the case of the first demonstration, a lot of things went into curation of the data, and also the architecture of the model. And so those were two kind of things that were novel about this. In the case of the NVIDIA example, a lot of work went into trying to use data from simulation, especially because collecting data on humanoids is quite challenging, and trying to figure out how to leverage that simulation data. In the case of the Figure example, there was also some architectural design choices that made it helpful, especially in terms of running models at very high frequency. And in the OpenVLA example, that was also an example where there was a lot of architectural choices in terms of the models. And so it's not just exactly what we talked about, so there is a bit more to it. But what we talked about is a huge driving factor behind these different examples. And these two, a lot of it also went into different like co-training objectives and architectures. So we've talked about a lot about how to train models with imitation learning. And there's one important thing that we haven't covered yet, which is what can go wrong and why imitation learning is kind of challenging. So for this, it's helpful to look at supervised learning. So in supervised learning, we have some data, and it's usually kind of trained from one data set that stays fixed. And we try to, and kind of the inputs to the model are completely independent from the predictions that the model makes. Now, this all changes in imitation learning. So say you have a demonstration that is in your data set. And so each of these dots is like a state, and then an action, state action, something like this. And now you're trying to mimic this demonstration. If you're trying to mimic it and then you roll out your policy, starting from this state, maybe at the beginning of the trajectory, it's able to do pretty well. But at some point it might like make a mistake. The policy isn't going to be perfect. And so if it makes a mistake, maybe it kind of ends up over here a little further from where the demonstration covered. And now from this state, it's possible that it actually doesn't have that much data from where it ended up after it made this mistake. Even if it was a small mistake, it's going to be kind of potentially underrepresented in the data. And if it's underrepresented, it's actually even more likely to make a mistake in the future. And so if it's more likely to make a mistake, it might actually kind of drift away from the distribution even more. And at that point, maybe here it's actually very far away and it makes maybe an even bigger mistake. So this is often referred to as compounding errors because these mistakes, because you can start drifting off the distribution when you make mistakes, those mistakes can then compound as you roll out your policy. And as a result of this, and kind of one thing that you see here is that the distribution of states, the distribution of states that are visited by your policy is actually different from the distribution of states that's visited by the expert. And this means that it differs fundamentally from supervised learning. So errors can lead away from the distribution. Errors can then compound. The states visited by the expert are different than the states visited by the learned policy. This is referred to as covariate shift. So it's a kind of distribution shift. And that sort of distribution shift can lead to worse performance. And also makes it different from supervised learning. So this is one of the reasons why fitting the distribution really well is very important. Because if you don't fit it well and you learn only the mean, for example, then you're even more likely to have these kinds of compounding errors. But even if you do fit it well, you might still make mistakes and might drift off the distribution. So how can we address this? One solution is just to collect a ton of data, train for as long as possible to fit the data as well as you can, and hope for the best. If you have the capacity to do this, it's not a terrible solution. But there's also some other solutions. And these solutions are actually quite popular in practice. And basically the key alternative solution is to try to collect corrective data. And so if we're in this scenario, what we can try to do is, as the policy starts to make a mistake, we could try to say, okay, if you're here, the correct action is to do this. And this kind of green data can be very, very helpful to allow the policy to recover from mistakes that it made. So the corrective data would be kind of ideally, you would learn kind of something like this that tells your policy exactly how to recover. And then if you collect this corrective data, then you could combine the data in green with the data in black, train a policy on that combined data. And then if it makes a mistake, it should actually have examples of how to recover and get back to the distribution. Because we're actually running our policy and then getting examples of how to recover after running our policy. does this not overfit the model and make it less generalizable? You would need to make sure that when you collect online data, you collect it in diverse scenarios and not just very narrow scenarios. If you only collect it in a very small amount of scenarios, then these corrections won't be as diverse as your original data set. Yeah, so the main difference between the learned policy distribution and the expert distribution it is just kind of how the actions led to particular states. And the reason, and this is, I'm kind of using this as shorthand for the states visited by the policy. And when you start to incorporate these corrections, you're kind of expanding the distributions of states that you have data for, and you're kind of making your data set, your distribution of states seen in your data set wider to include kind of both P of S and the states that your policy might be likely to visit if it makes mistakes. So in terms of what this looks like as an algorithm, we will first roll out our policy. So this is what's shown in blue here. Then we will query an expert at the states that you visited. And these actions in green are the same as kind of the orange A star on the slide. And then we will aggregate the corrective data with the first demonstration data set. And then we'll update the policy on the aggregated data set. In this updated policy, you could kind of fine tune the policy. So kind of warm start it, trained on the original data set, and then update it with fine tuning. You could also train from scratch if you're concerned about, I don't know, some biases or something like that. Oftentimes you might fine tune. And then you can actually repeat this process. So you can train on the corrective data, get a better policy, and then maybe your policy actually starts making, you have kind of another policy, and maybe it makes mistakes in a different way. And in that case, you'd want to then kind of collect some corrective data from that second policy if a new failure mode or a new kind of mistake emerges. And so this is a sort of repetitive process. This name has a terrible algorithm because it's not very descriptive, but it's called dataset aggregation, or DAGGER, because you're aggregating data. It's important and helpful to know terminology, but this is, I think, was a bad choice. And it's a data efficient way to learn from an expert, but it can be hard to query an expert. And so getting these green actions can be a little bit tricky. So you might have to actually ask a person like, okay, this is what my car did on the road. Like, what steering command should it have done instead in those scenarios? And so this sort of data actually can be potentially very hard to collect. Yeah, so how do we get the corrective data? What this would look like is you would run your policy to get this blue trajectory. And so this would be this trajectory is like a sequence of like S1, A1, S2, A2, and so forth. And then you would basically this is not possible in some scenarios, but you'd ask a person, like, for this S, what should the A have been? And for this S, what should the A have been? And for this S, what should the A have been? Now, there are scenarios where you can't do that, and where this algorithm is just not possible to run. And that kind of leads into potentially a scenario, like another way that we might be able to collect corrective data. We might not be able to tell exactly, like, this is exactly the steering command you should have done, because that's very hard to do. And so what we could do instead is, instead of saying, like, for each of these actions, we want to query what the expert would have done, we're actually going to let the expert take full control at some point. And so what this would look like is something where you start drifting off. The expert notices that a mistake was made and then takes full control. For example, starts driving the car rather than letting the policy drive the car. And then in this case, you can then add those kind of partial demonstrations to your data set instead of trying to query the expert on the policy states. And so here you would start to roll out the learned policy. The expert intervenes when the policy makes a mistake. The expert provides a partial demonstration from the state that the policy visited. So it would take full control and then aggregate this partial demonstrations with the original data set in order to then update the policy. And again, you can kind of repeat this process so that you can cover different potential failure modes of the policy. Yeah, so in all of these cases, the the best performance of the policy is upper bounded by the expert. The question was, if we're detecting a mistake, is that mostly if you've collided with something or something else? This is something that's subjective and is kind of up to the demonstrator in many ways. Oftentimes you want to be a bit more proactive, and before the car hits something, you would want to take control. And so one of the downsides of this algorithm is that it can sometimes be hard to catch mistakes quickly. Like if the policy decides to drastically change the action and it was unpredictable, that can be very hard to proactively prevent. And you want ideally this to be in a scenario where you can predict, like if the policy is starting to drift into another lane, kind of recentering it, that sort of thing. This is actually something that companies do in driving, where they let the policy run, they have a safety driver, and then the safety driver will take full control if it seems like the policy either doesn't know what to do and it's like stalling, or it's starting to make a mistake. Now, we've seen failure modes of that. We've seen cases where safety drivers were not able to prevent a mistake that was more major. And so there's downsides to this kind of relying on the demonstrator to proactively prevent a huge mistake from happening. But it is a practical interface for providing corrections in a lot of scenarios, and can help improve performance significantly. Yeah. So the question was, can you explain again why, if you're correcting a narrow corrective data, why that would lead to overfitting? So let's take the driving example. If your original driving data was like all over the United States, and then your corrective driving data was only on Stanford's campus, then when you combine the data set, it might only learn kind of that corrective behavior in a more narrow set of scenarios, and might also overfit to the Stanford data, leading to a policy that is perhaps less generalizable. And ideally, when you collected corrective data, it would be in a broader set of scenarios than campus.